Hello everyone, so today we're going to be talking about black holes. This will be part one of two videos, and this is in spirit of the recent picture that has surfaced in many news articles. You've probably seen it already, but I think it's important to really understand the significance of this picture to understand just a little bit more about black holes, like how do they form, and in this video, and also in the next video, I'm really going to focus on the math behind them because that's really the most important part. We never would have been able to obtain a picture of a black hole without understanding the mathematics behind them. And that's really what they're all about. So in this video, I'm going to talk about how they form, a little bit of math with that, some basic concepts to really help understand the nature of black holes, and then in the next video, we're going to use that information to talk more about the example of the black hole that is going around in the news lately, and make some calculations of our own, but I think are pretty neat because you can't find them in any articles. So to start off with, we need to know, how do we even get black holes? And in simplest terms, it's just when a star dies. But before it goes through that process, in the core of a star, there's something going on known as nuclear fusion. And so what is that? Well, in this case, you're taking four hydrogen nuclei. The nucleus is the center of an atom, and you're fusing them together. It's under very intense heat and pressure, and you end up with one helium nucleus. So one tangent I will go on in this video is talking about E equals mc squared, because you've probably heard it before, but maybe you don't really know what it means. And essentially, it's the mass-energy equivalence. So what do I mean by that? Mass and energy are kind of the same thing. You can convert from mass to energy and from energy to mass, and this equation explains the phenomenon where the mass of one helium nucleus is actually slightly smaller than the mass of four hydrogen put together. And the reason for that is because as you're going through this nuclear fusion, some of that mass is converted and lost as energy. And because of this energy, you're getting this radiation that exists around the core of the star. That's why they're so bright. It's in the form of light, it's in the form of radiation. So that's what's going on in stars. Well, eventually, these stars are going to run out of hydrogen to fuse. Nuclear fusion can still continue, but not in the same way. So what's going to happen is the star is going to expand and become very large, and it'll turn into something known as a giant or a supergiant. But why does this occur? Well, normally, there's this balance between, this is my radiation, this is the core of the star. There's this balance between the outward radiation happening because of nuclear fusion and the inward force of gravity. So when you run out of hydrogen, you're emitting radiation at a much lower rate. And because of that, gravity's taking over. So the core is going to be under a lot of pressure. It's going to raise to a very high temperature, and so nuclear fusion will continue. But what's going to happen is your helium is going to start to fuse into heavier elements, and this is something known as helium capture. And so what I've drawn here, you can think of it as an onion of nuclear reactions. So you're fusing helium, you get carbon, you start to fuse carbon, you get neon, you fuse neon, you get oxygen, and that's just going to keep happening and happening. And then your star is going to start to expand all the way out here. And eventually this process does end though. It ends with iron. Iron is not going to generate any more energy. So once you get to iron, nuclear fusion stops, and one of three things will happen at that point. When nuclear fusion stops, what ends up left behind is the core of the star. So there's a pretty simple rule that you can use to figure out what's going to happen from this point. So if the core left behind is less than 1.5 times the mass of the sun, that's just how you denote it, you're going to get a white dwarf. If it's between 1.5 and 3 solar masses, you're going to get a neutron star. And if it's greater than 3 solar masses, going to get a black hole. And the best way to compare these three is through looking at their relative densities. The formula for density is mass over volume. So mass is just how much matter something has, and volume is how much space it takes up. So looking at white dwarfs, they do have a very high mass. Not as high as neutron stars or black holes, but still a large mass. And they take up a very small volume. Again, not as small as neutron stars or black holes, but so they're going to have a pretty high density. I had to abbreviate there. Looking at neutron stars, they have an even higher mass than white dwarfs, and they take up an even smaller space. So looking back at the formula, you can see that's going to get us an even higher density. And then looking at black holes, as you can probably tell, they have a huge mass, even larger than neutron stars and white dwarfs, more than 3 times the mass of our sun, and they take up a very, very, very small volume, even down to the single point, and that's called the point of singularity. So they have a very, very high density. And so the next thing we're going to look at, to help us better understand what's going on with black holes as far as density goes, is looking at the limits of this equation. That might sound familiar if you've taken pre-cal or calculus. If you haven't, that's okay. It's still pretty simple to understand. So with limits, we're looking at what is happening to one variable in an equation when another is approaching a certain number. So in the case of our black holes, the volume is kind of approaching 0. Like, it wants to be really, really tiny, assuming that, the mass is just some whole number. But you might recall that you can't divide a number by 0, so your volume is never going to be 0, but it's going to get very close to 0. So we can kind of write it like this and say that our volume is approaching 0. And so the best way to look at this is thinking about a number that is very close to 0. So that would be like 0.00001, just infinite zeros and then a 1 at the end. The more zeros you add in between that decimal and that 1, the closer you are to 0. And we're not worried about mass. What we want to know is, as volume is approaching 0, what's happening to our density? So to better visualize this, at the bottom here, I just wrote that your mass is 5 whatever, and then your volume is a very small decimal, and that decimal, as it's approaching 0, you're going to have more zeros in front of that 1. So another way to represent that decimal is 1 over 1,000, 10,000, a million. That denominator is just going to keep getting bigger and bigger and bigger. And so if you have, I had to clear up some space, but so to rewrite the decimal, you have 5 over 1 over some large number. The rule keep, change, flip tells us to keep the numerator, to change the division to a multiplication sign, and to flip the fraction on the bottom. So when you're dividing 5 by 1 over whatever number, you're actually multiplying 5 by that denominator. So as the 10,000, the 100,000, the million, this number keeps getting bigger. I should probably write this. This equals density. So your density is getting increasingly larger as this fraction gets increasingly smaller. And so we can say that the limit as volume is approaching 0, our density is approaching infinity. It's just going to keep getting larger and larger and larger to infinity. And so going back to black holes, that's exactly what's happening. The volume is very, very tiny. It wants to be really small. And as it absorbs more matter, I mean, it's going to get bigger. But you have a very small volume, and the closer your volume is to 0, your density, assuming the mass stays the same, your density is just going to skyrocket. And so moral of the story, black holes are extremely dense objects in space. The final thing I'm going to talk about in this video is escape speed. So what is escape speed? It's the speed at which an object can quote-unquote escape the gravitational pull of another object that's at rest. And so you can use this for any two objects, but generally we're going to be talking about two planets, or a planet and a smaller object like a person. So what I've written here is the formula for escape speed or escape velocity. Either one is fine. So that's actually going to equal the square root of 2 times the gravitational constant. All you need to know about that is it's a number, and that number is going to be used every single time you use this formula, times m, which is the mass of the object that another object is trying to escape from, and finally that's going to be divided by the distance between those two objects. So what I've drawn here is something to help you visualize this a little better. So say this is our Earth and this is you on Earth, and you've learned to fly. Great job, good for you. So you're hovering above the surface of Earth, and your escape speed from Earth is going to be the speed at which you can fly away from the Earth and basically escape its gravitational pull. Gravity will still exist between you and the Earth, but it's essentially the speed that you need to attain at really any distance from that object, a given distance, I should say, in order to move away from its gravitational pull. So when you're thinking about spacecraft, they don't really ever achieve escape speed. They just use propulsion to get out of Earth's atmosphere. If they had attained escape speed, they wouldn't need any propulsion systems. They would just travel at one constant speed out of the atmosphere of Earth and into space. So how does escape speed relate to black holes? Well, a black hole can exist in any location where the density of matter is so large that the escape speed around this location equals or exceeds the speed of light. So what do I mean by that? Well, you have your black hole somewhere in space, and around the vicinity of this black hole, there's going to be a certain escape speed. And that escape speed is either going to be equal to the speed of light, so only light can really escape it at that point, or it's going to be greater than the speed of light. So at that point, nothing can escape it. And you've probably heard that no light can ever escape a black hole. And that is true, but it's not the whole story. And I hope that you return for the next video, because we're going to get into why that is and do some of our own calculations. So thank you for watching.